Then. Welcome everyone to the Astronomical Society of Edinburgh in our virtual mode. My name is Mark Phillips. I'm the president of the society. Welcome wherever you are in the world. I know we've got people from all over the world watching on YouTube now, and we have some special guests with us on Zoom as well. So welcome. I'll not keep you very long. We've got a few introductory slides, and then we'll get on to the main event of the evening with a talk by Dr. Bruce Vickery, which is quite a special occasion for us here. Just briefly, we have a couple of new members who have joined us this week. So Alistair Bruce and David Harvey, if we could all welcome in the usual way, we can unmute and welcome them. And as you can see, it's very cheap to join a society if you really want to do that. And a quick reminder for members, your renewals are due on the 1st of October. But if you joined on or after the 1st of April this year, then you've got another year before you have to pay. As we have quite a few new people on, new guests and so on, I thought I'd give a very quick rundown of who we actually are, in case you don't know. We were formed in 1924, so we're approaching our centenary, but really our roots go back to about 1811, and the roots of astronomy in Edinburgh in general go back to that same time, and we're part of that. We have 147 members as of this week. We normally do 2 public meetings per month. From next month, one will be a physical but hybrid meeting where we'll be in our usual place in Edinburgh, but broadcasting live on Zoom and YouTube. And we have one in the middle of the month as well, which will be virtual and viewable from wherever you are. We have a very active imaging and observing group where people meet together, chat about what they've been doing, share their images and observations, and learn from each other. And that's become really active, and people are taking some amazing images now in the society. We have 2 honorary presidents, Professor Andy Lawrence, who's the Regis Professor of Astronomy at Edinburgh University, and the new Astronomer Royal for Scotland, Catherine Haymans. And we work quite closely with these people. They're not just names on our website, but are actually people we work with. And we do run an outreach program, a 4-step outreach program, which runs at various points throughout the year to help people get into astronomy. And outreach is quite an important part of who we are and what we like to do. So that's who we are. If you want to keep an eye on what we're doing, there are various ways of staying in touch through our website, our Facebook page, Twitter feed, and all the videos of our meetings and talks are on our YouTube channel. You can see all our past meetings there. We've had quite a lot of amazing ones over the past year or so. This is what we've got coming soon. As I said, the 1st of October, that's our first physical meeting since the pandemic started. We will be in the Augustine United Church in Edinburgh, but we'll also be broadcasting online. And we have Mike Shaw from the USA for that one, coming in to tell us about astral landscape photography. 6th of October, for members only, we have our imaging observing group. And middle of the month, we have a talk about asteroids from Dr. Martin Elvis, how love, fear, and greed will determine our future in space. That'll be about space asteroid mining as well, I think. The 5th of November, we have Dr. Justin Campbell-White, actually in person from the University of Dundee, talking about accretion disks of main sequence stars, pre-main sequence stars. And on the 19th of November, we have Mr. Comet himself, David H. Levy. He's going to tell us basically his biography, I think, A Night Watchman's Journey, The Road Not Taken. That should be really fascinating. So this is what we're all here for today, this special talk by Bruce Vickery. Andrew Farrow is going to introduce the talk, and then I'm going to hand over to Bruce, who will take the floor. Thank you, Andrew.
Thank you, Mark. I think, as we said on our website, astronomers love a conjunction. Of course, we're normally referring to celestial bodies appearing to get closer in the sky. Whereas tonight, we have a conjunction of astronomy and archaeology, or perhaps more precisely, probably celestial mechanics and ancient history. Bruce is well known in the AAC for his talks about historical figures and events in astronomy. But tonight, I think is actually making a bit of history himself with his solution to the long-standing issue of interpreting the Venus tablets. Following the quest he started in I think 2014, I think tonight's a tribute to his determination and the solution a testament to his skill as a mathematician, a logistician, and a software programmer. Following the talk tonight at about 9 o'clock, the paper that Bruce has written describing in detail what he's done will be published on our website. So it'll be there for anybody to look at and download. A reminder that anybody on Zoom who has a question, if you put that in the chat box, and as normal, Peter will call you out and you can ask those questions of Bruce. If you're watching the live version on YouTube, please put your questions in the comments section, and we'll be monitoring that and hopefully we'll ask them on your behalf. And with that, I'll hand over to Bruce.
Okay, Bruce, you can share your slides now, please. And you're muted, Bruce.
Yep.
Right.
Okay. I think I'm unmuted now.
Yep.
I just want to minimize the number of people I'm seeing because that gets in the way on my screen, and then I can start. Well, thanks for your introduction, both Mark and Andrew, and everybody else, and those. Welcome to the talk. I gave a talk not too long ago on this particular subject, which I had resurrected after looking at it some years ago, earlier this year. And since I gave that talk a few months ago, I've made quite a significant breakthrough, which is what I want to talk about here tonight. And that breakthrough came directly from mathematics. The interesting thing is that the very first time I was told about this particular tablet, which we see here, it's at the British Museum. The very first time I was told about it, my first instinct was, oh, that's just maths. You know, it's just where the celestial objects are. It's really nothing to do with archaeology, apart from the fact that it is archaeology. And so I've now gone through a mathematical solution since the last talk, which I want to report here tonight, and I'll be telling you exactly how I went about it. For those who are slightly unfamiliar with the tablet, it was written during the reign of King Ammisaduqa. And if we can solve the dates of the astronomical observations that are written onto this tablet, we then know when Ammisaduqa was on the throne. And that's helpful to the archaeologists and historians of the time. So the challenge is to take 50 individual astronomical observations on a clay tablet from ancient Babylon and find where they fit into the Julian or the Gregorian calendar. Now, I put both there because the algorithms I'm using give me dates in the Julian calendar. So everything I say tonight that's a date is a Julian date, but the Gregorian calendar is only a couple of weeks different, even back at these times. The observations consist of 25 settings of Venus and 25 risings of Venus over a 21-year period, which is believed to be Ammisaduqa's reign. There should be 26, but one has been overwritten since the tablet was created, and so we only have 25 left to look through. Research, it was found around the 1850s in Mesopotamia, and there's more than one copy of it. There is only one tablet, but there's more than one copy, and they're all broken for various reasons, historical reasons, but they're broken in different ways, so it's been reconstructed extremely well. And over the last 100 years, since 1920, when researchers started to look at this tablet seriously, we've arrived at a point, it seems to me, from my readings of the web, where Ammisaduqa's accession to the throne was one of four favored dates. 1702 BC, which is the high chronology, 1646 BC and 1638 BC, which are the middle chronology, upper and lower, and finally 1582 BC, the low chronology. When I started 7 years ago, I actually didn't really know this information, and I found that there's a repetitive nature to the way Venus behaves in its rising and settings. And I decided at that time that it probably was impossible to solve. However, now that the dates have been compressed down to that period of time there, which is only about 120 years, it's easier to actually tease one out that might be the right one, because it has resonances at various dates. The application of Venus at the setting and rising, but we're only looking at a small number of dates now, and it's a little bit easier to unpick it. For me, the enabling technology to actually do this work is this book here, Astronomical Algorithms, written by Jean Meus, and it dates from the late 1990s. Jean Meus has been very active in astronomy for all his life, and in this book, he presents one of the best celestial theories at the time when he wrote the book. It's called VSOP 87D. 87 was the year in which it came to fruition, 1987. And this was the bee's knees at that time, and you can get extremely accurate results from it. And I'll explain how accurate fairly soon. And I programmed that from this book, and it tells you where objects in the solar system were on the celestial sphere at any time back to 2000 BC and forward to 6000 AD, which is more than enough for what we want, because Ammisaduqa was somewhere between 1580 and 1702. And for this challenge, we're interested in the positions of the Earth, the Sun, the Moon, and Venus in the date range 1650 BC, plus or minus 100 years or so. So that's the area that we're looking in. Now, I programmed all that up. In fact, I've been using Meus's book since around 2011, 2010. So I was already several years into the project that I was doing, and that was just creating interesting astronomical suite of software that I could play with, so to speak, when I discovered this particular problem. And my immediate reaction was, knowing how accurate these routines were, was that I could solve it. And the accuracy of my solution depends on two things. One, the accuracy of the theory that is in the book, and the accuracy with which my analytic software correctly reflects that theory. But the reality is I can't unbundle these, so I have to look at the answers I'm getting to see if they are stacking up with modern theories. Now, NASA, every time it sends a rocket up, goes back and adjusts all of their algorithms. So bit by bit, these algorithms change. And we're now over 20 years since Meus published this book. But there are big data sets on the web which are more modern, and they've been put there by Fred Espenack, who works for NASA, and Jean Meus, who's the writer of the book, and he does a lot of work for NASA as well. And they've been using more up-to-date information than I have to position the celestial objects. And what they've put on the web here, and you can download it quite easily, a 5 millennium canon of lunar eclipses. That's from minus 2000 BC to 3000 AD. A 5 millennium canon of solar eclipses, also 2000 BC to 3000 AD. And a 6 millennium catalogue of Venus transits, again 2000 AD, but goes to 2000 BC, sorry, going to 4000 AD. And that covers the dates that we're interested in for Ammisaduqa. And so my calibration, so to speak, was to calculate the position of Moon and Venus compared with the Sun over dates that are relevant to the problem at hand, but I can check in these tables. I didn't use the solar eclipse canon. Solar eclipses are far more complex than lunar eclipses, and these are the easier ones to deal with. So here's my results for the lunar eclipses when I did the comparisons. I selected 1650 as the central date, went 100 years back and 100 years forward. And it's not exact because I then searched for a total eclipse of the moon in each case. Why? Because a total eclipse is very precise. The three objects have got to be in line for that to happen. And therefore, if I've selected a total eclipse, I'm giving my software a pretty tough test. And as it turns out, Espenac and Mias, for example, for this first one, 13th to the 8th, minus 1751, they predicted that total eclipse would be at its greatest point at 2:35 a.m. I got 3:10 a.m., so I'm only 35 minutes wrong there. All of the other parameters of the eclipse, which I don't put into this table here, were very similar to their parameters. And for the second and the third ones, I'm a little bit worse, 1 hour 54 here and 3 hours 08 here. But that's not a lot. So let's say on average, I'm about a tenth of a day out. That would be 2.4 hours. So what kind of an error would that result in over the period of time that I'm trying to solve these tablets? Not a lot. It means probably that about 10% of the time I will be 1 day wrong in the visibility of the lunar crescent because I've got one incorrect day in terms of when the new moon occurred, which you start with. So that looks pretty good. Venus transits, they are more rare than eclipses, of course. They operate in pairs at about 100, 112, 114 years. So there are only 4 in the region of the dates that I'm looking at, one of them at minus 1755 BC. Now, Espenac only did this table, and he said that, a transit, incidentally, for those who don't know what a transit is, a transit's when Venus not only just comes past the sun, between us and the sun, but it actually comes past us, and it's in line of the sun, so we could see a black dot on the sun as it goes past. It doesn't happen very often, as I say, about every 110 years you get a pair. So for this one, Espenac said it would be closest to the center of the sun at 1417 on that day. My algorithms gave me 1359, which is only 18 minutes correct. He said it would be 7.9 minutes of arc away from the center of the sun, so it doesn't pass right through the center. I got 2.9, so I'm 5 minutes of arc out on that one. And so on through these 4 here. And I'm between a quarter and a half an hour wrong in terms of when Venus was actually literally in front of the sun, and between 4.7 and 9.2 minutes of arc in error in its position in front of the sun, just not a lot. Now, how is this error going to affect us? I'm going to show you shortly, and I think I did it in the previous talk as well, that superior conjunctions are long conjunctions over 2 months long, and inferior conjunctions are short conjunctions between 3 and 10 and 20 days. So inferior conjunctions are quite quick, and superior conjunctions are quite slow. And what this means is that at an inferior conjunction, Venus is moving around about 1.6 degrees per day with respect to the sun in the sky. That is 10 times this number. So for inferior conjunctions, it is unlikely the errors that I've got are going to have any effect whatsoever on the solution. It's 24 minutes here, and we're going up by a day at a time, and you'll see what effect that has when I demonstrate it shortly. However, for inferior conjunctions, this bottom number of minutes of arc here is around about a half of the distance that Venus moves in a day with respect to the sun. So we've got a significant problem there for superior conjunctions, and we can easily be a day wrong at this level. But I'll show shortly that they are so difficult to actually find the setting and rising dates that I did not include them in any of the analysis I did. They are very low precision data points. Before I show you the dynamics of this, just want to run through Archivisionus again, because I found a problem with Archivisionus when in the last couple of months. Archivisionus is the name given to the possibility that we can see a crescent moon above the horizon at sunset or above the horizon before the sun rises. And it depends on how dark the sky is, of course, and how far away the moon is from the sun. The darkness of the sky is dictated by the height of Venus above the center of the sun. So we could have a fairly bright Venus at a lower height or a dull Venus at a higher height. Whereas the arc of light, which is the other angle, is the angle with respect to the sun of the moon itself. That dictates how big that crescent is, and therefore how bright it is. So if the moon is quite some distance from the sun at first crescent time, we'll see it earlier at a lower arc V than if it's not. And there's an algorithm that links these two parameters that's been studied over more than 100 years, I think. But the current one that I found on the web, which I believe is the latest, was published in 1990 by a man called Yallop in the UK, in fact. And I've used that, and I think some of the other researchers are doing the same. So with the accurate algorithms of Mias and the algorithm of Yallop, I can create a very, very precise Babylonian calendar. Because as you know, each month in the Babylonian calendar starts when they see that crescent. And that's also true of Islam to this day. So it's of very great interest, which is one of the reasons a lot of research has been done here, I think. Now, Venus is a different kettle of fish. And Venus is so far away compared with the moon that even though it takes on a crescent shape at inferior conjunction as it moves away from the sun, it doesn't at superior because it's full. At inferior conjunction, it takes on a crescent. Now, all researchers up until now have said, no, the only parameter you need is the arc of vision, which is the perpendicular height of Venus above the sun. And when that reaches a certain value, Venus gets extinguished. I'm going to challenge that view in a moment. So let me have a look at, I'm going to change screens here to this screen here. And I'm going to show you something about the orbit of Venus. And then I'm going to show you some actual movements against the backdrop of the sky to reinforce what it is I'm talking about here. Now, if I start this running, what we've got here, sorry, I'll pause it first. That's the sun at the center. Here's the Earth moving on this red orbit, and here's Venus moving on the yellow orbit. So let me just resume that. And eventually we're going to come to a point around about here when they're in a straight line. That's a conjunction. And in that straight line, we have the Earth here, the sun here, and Venus is between the Earth and the sun. So that's an inferior conjunction, and Venus looks black. And I've drawn this geometrically to the size that we will see Venus at. Try to remember how big this black circle is, because you're going to see something different fairly soon. So as Venus pulls away from that, and I'll stop it shortly, we see a crescent building up on Venus as it pulls away from inferior conjunction. That crescent is so large in size, like the size of this black image here, that it's brighter than when Venus is further away from the Earth at superior conjunction. So we see Venus quite easily at inferior conjunction when it pulls away from the sun. Now I'll go around to superior conjunction, which is the next thing that happens, and we'll see slightly different. Watch how Venus is moving away from the Earth. And when we get around to superior conjunction, it's fully lit, so it's full. And unlike the moon when it's fully lit, which is a lot brighter when it's dark, than when it's dark, Venus, that black circle that we saw when it was close to the Earth, and the very crescent on it, is brighter than it is when it's full over at this distance, which is more than 6 times away from this point here where it is at inferior conjunction. So at superior conjunction, we have a slightly duller Venus, a bit more difficult to see perhaps, and it's quite different from inferior. And it's different in another way in that it's moving slower here. I want to change at this point to having the Earth at the center. So imagine us on the Earth here, and we're looking at the Sun and we're looking at Venus. And this is, I just moved a moment before I stopped it again. We're still in inferior conjunction here. Now, when I start this running, you will see that the Sun and Venus are both going anti-clockwise, right? So they're both going anti-clockwise. So at superior conjunction, Venus and the Sun are both going anti-clockwise. Venus catches up with the Sun and passes it. But now when we get to inferior conjunction, and I'll stop it in a moment. There we go. When we get to inferior conjunction, something different happens. Not only is Venus a lot closer to the Earth, 6 times closer, 6 times bigger. You see there's a little arc still there. We can probably see Venus at this point here. For 40 days, and I've colored it red here, and you may have seen it earlier, for 40 days, Venus goes in the opposite direction. It goes clockwise compared with the Earth and the Sun. It's to do with the difference in speeds of the orbits. And so if you watch this closely when I start it again, you'll still see the Sun going anti-clockwise, but you will see this line going somewhat clockwise before it turns around again. So it's going clockwise at the moment. And as soon as it starts to go anti-clockwise again, I make it yellow, like there. So what we have at inferior conjunction is Venus and the Sun crossing each other at different directions. It's very fast. But what we have at superior conjunction is they're both moving in the same direction, but Venus is going a bit faster, slow. It's like overtaking cars on a road. When you go past one going the opposite direction, it's quite quick. When you try to overtake one, it's quite slow. And this comes into play. I now want to show you visually how Venus behaves at conjunctions. Now, this map is actually the map at this very time here. When I enter this piece of software, it picks today's date and time. This is the time in Babylon, incidentally. So I have here, and I'm going to draw this always with the Sun on the horizon, which is the white line. Sometimes it'll be the morning sky and sometimes the evening. The green line is the ecliptic. That's the plane in which the Earth and the Sun are always attached to. And the planets are quite close to that ecliptic. They don't go very far away from it, but we always stay on it. And I've got a feature up here called declutter, whereby I can take everything off that we're not interested in. We're only interested in the Sun, Venus, and indeed the Moon. And they're the only things that you'll see here. And since Venus isn't around at the moment, we don't see it on this map. But what I have here are a lot of my databases, which I prepared earlier, shall we say, and I'm going to pick one out. My eyesight's not too good. And this is the database that relates to 6 degrees for arc V, i.e., when Venus is at 6 degrees, we'll see it. Above the horizon, we'll see it. When it's below the horizon, below 6 degrees, we won't see it, even if it's 5.99, because this is maths. It'll say that can't be seen. At 6.01, it will be seen, sort of thing. So, and I want to go to one of the conjunctions. These are all the conjunctions that happen between 1500 BC and 1800 BC, and I'm looking for one particular one, which is on the 12th of October minus 1635. That's a date that's common to the 2 middle chronologies, but I could have picked other dates. The effect that I'm about to show you is common to all of the dates. It's the way the whole thing operates. Let me look at sunrise for that conjunction first. Here's this is the date of the conjunction, the 12th of the 10th. So if I go forwards in time now, we see Venus rising after the conjunction. It's below the horizon here. And to go forwards, I can go one day at a time, forwards and backwards up here. I'll go 5 days. 1, 2, 3, 4, 5. Now, did you see how Venus jumped in quantized jumps? Because we're going through a whole 24 hours here before we see it again. And it's 1.6 degrees further up. And so in 5 days, we've gone from below the horizon here to 7.15 degrees above the horizon, and we can now see it according to the mathematical calculations I'm doing. And if I go back 1 day, it's 5.56. We won't see it. So my software is going to say that's where you'll see it. Just take note, incidentally, this other number here, which is the arc of light, 9.33, that's the distance between the center of the sun and the center of Venus. And if that was 0, we wouldn't see anything, it'd be black. But it's 9, there's a little bit of the light on this side of it here, a little bit of a crescent. I now want to show you what happens at the setting time. This was rising. Let's go to setting for that same conjunction. Here's the conjunction point. I've got to go backwards now because setting it came along and arrived at this point. I'm going to go backwards 2 weeks. That's 14 days and not the 5 I just did. Notice how Venus was running roughly parallel to the ecliptic, which was now at an acute angle. It's not perpendicular. And so Venus wasn't rising up above the horizon all that fast. And in fact, at this point here, 4.82 degrees, my software is going to say, can't see it. If I go back 2 more, it's starting to go off the screen. But there we are at 6.13. My software is going to say, absolutely categorically, above 6 degrees, can see it. Let me come forward those 2 days again. Because the point I want to make here is the following. My software is going to say, I can't see that, it's below 6 degrees. However, the arc of light is 21.46 degrees here. So that's the distance between the center of Venus and the sun. That's more than double where we could see it when it rose here. And I would contend that that crescent is probably light enough for Venus to be seen at this point. In other words, what I'm saying is that you can't just say that the rising and setting of Venus is a function of arc V only, i.e. the height above the horizon when the sun sets or rises. It probably has enough light on it at inferior conjunctions. This won't happen at superior because superior it's fully lit. It probably has enough light on it at inferior conjunctions to be similar to the moon. Now, I can't find any literature that tells me this. Everybody's just assumed that it's been the other way. And indeed, a researcher called De Jong, who's a very careful researcher, some years ago, he analyzed the rising and setting of Venus using data that was about 1,000 years newer than this data. He didn't tamper with this data. And he has 4 different arc Vs for the setting and rising of Venus. One particular arc V for when it sets in the west, another one for when it rises in the east, another one when it sets in the east, another one that rises in the west, because he felt that he could, the data would become more accurate if he used that sort of arrangement. And right up until fairly recently, I was going backwards and forwards between using 6 degrees all round, so making no choice whatsoever apart from a constant arc V, just sometimes trying his one out. And the long and short of what happened to me was that using his 4 different values didn't give me any better way of finding a single result. I always finished up the same as what I was doing when I had 6 degrees only, or I used also 5, 5.5 and 6.5 just to keep the whole thing melting for a while until it sort of crystallized. And I couldn't see any different. And as a result of being concerned about this situation, that it is not related to arc V, but it is related to arc L, I took the decision to keep it simple and just use a constant arc V, rightly or wrongly. And I did that after I had spent a lot of time looking at the 4 preferred solutions on maps like this, going through every one of the observations for each one, 20, just 50, I think, or 22 for each one, and trying to imagine by eye looking at these numbers whether I might have been able to see Venus at that point or not. And it doesn't really work any better than just accepting that it's complicated and just use a simple solution, 6 degrees. Now, before I leave this, I just want to quickly show you a superior conjunction. Or before I do that, let me go back to sunrise and just remind you that when we're in sunrise, 1, 2, 3, 4, 5 days, and we can see it. Okay, now let's go to, this is a superior conjunction. Venus is moving slowly. So this time when I go 5 days, 2, 3, 4, 5, it's hardly moved. It's not moving fast at all. It's at 1 degree at the moment. So if I do, let me do 7, that's a week. We're still only 3 degrees. It takes ages to get to 6 degrees. And one of the problems of that is that it's in the vicinity of 6 degrees for quite some time. And you noticed on the inferior conjunction, it jumped from 5.5 degrees right past 7 and went straight through the 6s. So we know we're going to get a really good point there. But here, it's hovering in the same, roughly the same area for some considerable time. And that means that the Babylonians could have seen that at any one of those days, depending on the conditions in the atmosphere. And so I'm hypothesizing here, and De Jong actually agrees with me, he's put it in one of his papers, I'm hypothesizing here that superior data is not precise. We cannot, with precise mathematical calculations, get close enough to the answers they may have got that we can do a precise mathematical calculation with it. So I did all my work at 6 degrees of arc V and with no superior conjunctions in my list. Now I want to go back to the other screen here. Right, so we're back into the PowerPoint section now. So up to this point, I've given you a sort of a package of the sort of things I was looking at in the behavior of Venus, the behavior of the sun and the moon, sorry, and how I was putting together high precision data to deal with this. Now I want to show you what I was doing when I gave the previous lecture. We know now from the calibrations that I've done that these algorithms in the MIAS book are very good. They're high precision. That means I have created, in conjunction with the Aleph algorithm, of course, a high precision lunar calendar database. That's the calendar for Babylon in terms of months that began on the first crescent. I don't have the names of those months because this is a mathematical exposition. The names would have to be filled in by looking at the dates in antiquity and seeing what month it was. Having created that, which I do first, I then create a high precision conjunction database. This is the business that Venus is doing. I'm finding for that database, amongst other things, when the conjunction occurred, which I was showing you on that little simulation earlier, and also when my software says it goes below 6 degrees from the horizon and when it comes back up to 6 degrees at rising. So they're in the database, so I can compare them directly with the tablet if I have to. But I made a mistake, actually. We come down now to the tablet observations, and they are also, like the algorithms, high precision. Now, that's an interesting statement that I'm making, that I'm sticking my neck out. Why? Because if they're not high precision, it is impossible to solve this. They've got to be high precision. These observations have got to be what the Babylonians did perfectly, as far as they could do. Any errors in them probably would have been errors due to climatic conditions. They mightn't have seen Venus a couple of days when they should have seen it, or the moon, for example, might be 1 day out for the crescent, etc. because they're not operating with strict maths. They're operating with eyesight and the conditions in the atmosphere. So, but in terms of those parameters, my view is that these observations are high precision. So I took those high precision observations and I synthesized a calendar. And I described that in full in that previous lecture. Then I took that calendar and I compared it with this conjunction database to try to get a result. And the way I did it is what I'd call an elimination result. And I think this is probably fairly popular and it's probably done for the 100 years. You weed out all of the conjunctions that couldn't possibly be right. For example, the first entry on the tablet is an inferior conjunction. So you can't start with a superior conjunction. So half of your data's gone already. Every superior conjunction can't be the start of the tablet. Half of them gone. But then you've got things like there was a 3-day invisibility, and then you've got an inferior conjunction that was a 10-day invisibility. Well, it's not going to start on that particular inferior conjunction either, is it? So you jettison it. So it's quite easy to go through this mathematically with a little bit of slack in it to knock out observations that couldn't possibly be the first date on that tablet. And you could quite easily, doing this, get to inside 20 possible solutions, starting at about 366, in fact. So, and then you can even get lower. If you're very brave, you can get down to about 7 or 8. But I was concerned when I got down below 20 that if one of them, the one coming 18th, might have won it if I had kept it in. So you start to get a bit conservative here at this point. But the other thing that you're doing is you're now looking at each individual solution and comparing it by eye with the tablet observations to see if by eye you can find one of those that works. And it's not possible. But one of the problems is, I mean, you could do it if you started to imagine things. One of the problems is when you're doing this yourself and you're looking at the various calculations, some of them you're looking at and they say, well, that's a pretty good agreement there. I like that one. That's probably a good reading, et cetera, et cetera. And that doesn't look too good. So that's not a good reading. So you're starting to convince yourself to select ones that are good in some places and bad in others. And that doesn't work. It's emotional. So that wasn't producing a result for me for 2 reasons. One is this calendar is a lower precision than that. I was using a 29.53 day average for the months. Now, why did I do something as silly as that? Mainly because at the beginning, I thought that this is just a piece of maths and it doesn't matter if I've got the odd day wrong here, it's going to work. But that doesn't work because with the resonance between the orbits, you've got to really be very, very careful. And it doesn't take due account of that when you've started to get a low precision instrument. Now, at that talk, I didn't actually have this particular structure in my mind at that time. It's just the way I'd done it. At that talk, Horst Meyerdijks asked me a question. And the question was, had I compared the tablet observations with the high precision lunar crescent data? And I kind of had been rocked back on my heels. The answer is no, but the answer is sort of yes, because that high precision data comes down through this loop here. And at this point here, it arrives still in a high precision state. Unfortunately, because I've gone through this box and finished up with a low precision calendar, I'm then comparing a high precision data with low precision data, and the result was poor. So as a result, I went back to the drawing board, and it was very simple to actually fix this. I cut this out and that out. I've never looked at them again. And I'm now comparing high precision observational tablet readings with high precision data in my conjunction database directly. And I've got a mathematical algorithm to do that for me. And I ignore, as I keep saying, superior conjunctions. And that mathematical procedure is a method of least squares, which is something common to mathematicians. I've used it. I've used this a few times in my life, actually, in other jobs that I've done. Now, for those of you, and this is the elegant method I'm talking about, for those of you whose eyes just glazed over because you saw the word maths, just relax. I'm going to try to explain this so you understand it. And you can get me later if you didn't. Typically, we might be doing an experiment in a lab, and we're taking some readings. That's these red dots here. And we believe we're dealing with something that's linear in nature. And so we want to find the best straight line that covers that grouping, because there's little errors in all of these readings, you know, but we want a straight line. The way it's done is you take the value here that you measured, and you take the value on the straight line just below it at the same x value, you subtract them and you square that, and then you put it into an accumulator box, which starts at 0. So the first one goes in. Then you do it with the second point. You subtract these two numbers, square it, add that onto that number you've already got in the box, which is this one. You do it the third, fourth, fifth, fifth. So eventually you add up. Every one of those data points has got a different square from that straight line, and you add them all up. You get an answer, which is a figure of merit of how good that line is. Then you'll draw a different line, for example. This isn't quite how it's done, but it's easier for me to explain it to those mathematical people. You draw a different line, and you go through that process again, and you see if the summation of the squares you get is less than the one you had before. If so, that's a better line. And you might draw another line, etc. It's a very boring way of doing it that way, but mathematicians have a shortcut, which I haven't described. So that's what it's all about. You're looking for the line that on average is closer to all of these points than on any other line. Now, I put this across to our problem. We don't have a straight line, but what we do have are high precision calculations of the day of the month that I think things were happening from my software, and the day of the month that are on the tablets. So we can look at this graph here as though the red dots are coming from the tablets and the green dots are the day of the month. This first one would be the day of the month that Venus disappeared in the west. And I've got on my green point here the day of the month in my conjunction database that I think it disappeared when it was in the west. And so I subtract those to square them and pop that in my little accumulator box. And then the second one is day of month that it reappeared, day of month that I think it reappeared. Again, I subtract these two, square it, and add it into that box. And I do that all the way up for 22 individual values. I'm using 11 inferior conjunctions from the tablet. There are only 13 on the tablet. I've dropped 2, but I can explain why. I'm using 11 of them, which gives me 22 data points that I'm accumulating the least squares for. There were some of the squares. And I do that for every conjunction in the database, about 366 of them. It takes about a second on my machine, so that's why I do the lot every time. And then I find the one that's smallest, because that is the optimal solution to the problem. Now, I did that for 4 different ArcVs, actually, 5 degrees, 5.5, 6, and 6.5, just to give me a spread of interest. And I did it for the 300 years, which is a bit more than is needed, 1500 BC to 1800 BC. And 1645 won every time. It was always the top of the list. It had the smallest sum of squares of any of the other years where I worked the conjunctions out. And here's a summary of what I got for 1645 BC. At an ArcV of 6.5, I got a figure of merit of 122. And then 6, I got 103, 103, 112. I picked 6 as being, it's one of the lower 2, as being the angle I wanted. Just let me go through the columns one at a time here. This one here, this is a mathematical symbol meaning sigma, sum all these numbers. So I took the setting days of the month, both from the tablet and from my database, subtracted, squared them, and added them on. I did that for all 11 of those, and I got 81. Then I did it for the rising months, the days of the months, subtracted those, squared them, add them all up, got 41. And I added those two figures to get this answer here, which is the whole 22 results. And I did that for all 4 there. Some of the days invisible, do not be suckered into doing this. This is a very poor way of trying to find the best solution. Here I'm taking the sum of the days that I think it's invisible myself and the sum of the days they think it's invisible themselves, subtracting those two, squaring it and adding it up. But if you look at something like this one down here, which looks pretty good actually, 5.5, you can get a number like that for an absolutely awful result, because you can get results where the 2 dates are completely wrong, but the distance between them is the same number, like 3. So you're adding the same number on, but your 2 dates are way out of line. So this is an extremely insensitive number. I've just put it there for completeness and to be able to explain that to you, because I got a fright sometimes. I was seeing terrible solutions with like small numbers in them here. When you inspect it, the actual days were way out of line. So this is the one that came to the surface. And having selected 6.0, I'll now show you the winners, shall we say, the top performers at an ArcV of 6.0 degrees, with 1645 at the top, of course, is at the top of all of them. There's 11 items in this list because I arbitrarily sliced the list at 500 as being none of those are going to work. But what's interesting here is, and this is why it's so difficult to actually solve this problem, the date coming second, this is one of the pair of dates for the low chronology. And in fact, the one coming third is the other one. So the low chronology came second and third here. And the one that's come second is 151, which is not that bad compared with this, although we're starting to get out of line here. And by the time we get here, it's more than double. And I think we can decide that these ones aren't really going anywhere. But so that's the low chronology, but you can see here, this one here, 1709, that's the high chronology, and so 1701. And 1709 gets 218, and 1701 gets 306, so it's not looking promising. 1637, incidentally, which is the other pair of 1645, it's down here, and it doesn't do too well. So my favorite, of course, is 1645. And there's, when I get to the volcanoes, I'll try and reinforce this, in fact.
Bruce, can I ask a point of clarification?
Yeah.
On the previous slide,
That one there?
at the very bottom, it says 1654.
I apologize, I'm getting dyslexic.
Sorry, I assumed it was 1645 and you typed it 1654 at the bottom.
Oh, I do apologize. I hate to say it, don't get old. I'm getting dyslexic.
I beat you to it. I beat you to it, Bruce, but I didn't want anybody else to think something.
What I should say, Andrew, is that I put that in deliberately to see if you were listening. I apologize. That is a typo. Yeah. It is 645 BC. And as I say, 1637 doesn't stack up too well on this mathematical formula. But we have got the 4 favorites and a few other ones that are in years that we're not interested in. But there's some caveats to this, by the way. You don't just throw a least squares at a thing, and pray. You have to have errors that are assumed to be random and not systematic. So there is an assumption here that the validity of the answer I've got is dependent on the fact that the errors of the data points on the tablet, if they are errors, are random. If they're systematic, doesn't mean to say I'd get the wrong answer, but you would have to question it. The other caveat is that the modern celestial mechanics is up to the job. The only thing I can say is my calculations are so close to Espinac-Nias's that if I'm wrong, they're wrong, or if they're wrong, I'm wrong. But then everybody who's researching this is using the same up-to-date material. The positives that come out of this are really quite good, actually, because the one thing that mathematics does, it takes the human side out of the equation. You can't be accused of saying you got that answer because you like that particular observation, or you don't like that particular observation, sort of thing. You didn't put it in because you didn't like it, and this one got one. No assumptions have been made by me in respect of Babylonian history. That's not my stock in trade. I can't do that. And so it's quite interesting, if you think about it, that with mathematics alone and no emotion, no nothing, it got 1645 BC, which is a favored solution. And it's a favored solution amongst those other three because the archaeological fraternity has partly selected these because they fit with other things that they've discovered about what was going on in Babylon. I don't have that, but I've got the same answer. So that's one plus that I've got. The second one, and this is the one that takes the emotion out of it, no observation has been deemed more important than any other. I don't have a favorite observation on that tablet. Zero, none. The numbers were just thrown at the mathematics, and mathematics said 1645 BC. So there is no input by me personally in the arrival at that solution, apart from the fact that I programmed an algorithm that would do the business. All inferior conjunctions have been used, except one that may be related to volcanic activity, and I'll mention that shortly, and a second one that does not fit into any analysis procedure. That's the 19th year one. Man, everybody tears their hair out about that one. It just doesn't look right. And you can't even say the scribe left a 10 off or put an extra 10 on, which is the usual error. It's random. Now, I've got a theory about that, and that is that the previous observation line above this one on the tablet is the one that's been obliterated. It was a superior conjunction. It got written over, it was year 18, when they added something extra to the tile later than when the tile was made. And I'm half wondering if when they did that, they did some damage to the next one, which is the 19th year. And that's why it's a bit odd. But I can't prove or deny that. It's just an awful, awful observation. Now, you could argue, since I've said that we need random errors, to make the least squares correct, that's a random error, throw it in, But the problem is it's so far away from all of the solutions that there's a danger it'll damage one of those solutions worse than it should be. So I don't think it belongs in there, and I took it out. That means I had 11 of the 13 pairs of observations. Then I sat back. I was pretty happy. I was pretty excited at that point, incidentally, and when 1645 popped out, being as it's in the middle of the whole game. And I then thought, well, why don't I just throw this for 1,000 years and see what turns up? There might be something turns up. And something did turn up. I found a new harmonic or resonance point in the orbit of Venus and the Earth, 219 years. And here's the table that I got when I went from 1000 BC to 2000 BC. Our favorite solution, or my favorite solution, 1645 BC, only comes in second. I got a shock when I saw that before I started reading the top line here. Now, perhaps archaeology should look at this date, I don't know. It's quite a long way away. It's 219 years away, but it comes up with an 83. So I started thinking about this, and I thought, what's interesting about this is it's not a factor of 8. And all the papers that I've read, and everybody follows this rule, that when you've got a solution, you add 8, 56, 64 to it, and you'll get another solution. They don't tell you to add 219 to it and get another solution. So I looked at this and I discovered that the orbital period of the Earth, this is NASA figures. I took the 2 figures from NASA, so I took them from the same place. 365.242 days for the orbital period of the Earth, 224,695 for Venus. And we know that it's 219 years that's got a problem here, or a harmonic. So I multiplied those 2 numbers together and got 79,988.0 days, approx. I then divided this number here by 224.695 because I had no idea how many orbits of Venus it would be off the cuff. And I got 356 and a bit. So I truncated that to 356 orbits, multiplied these 2 together, and I got this number here, which is only 3.4 days different from the 219 orbits of the Earth. So we have an interesting new kid on the block here in terms of resonances between the orbits. I don't think it does anything bad to the results, but in fact, to some extent, this made me feel good because it made me feel that if my least squares algorithm is working out this far, at this far, that the observations on the tablet must be pretty good. They can't be kind of faked or incorrect in some way, because I wouldn't have found, the further I moved away from 1645 BC, I probably would have got worse results. So I was quite happy when I got this at the end of the day, but it just brings a new dimension to the whole problem. I now want to talk about the volcanic activity, which comes into this. Now, I hypothesized in my previous talk that it was the Santorini, well, let me just wind back slightly. 2 of the observational lines on the tablet stick out like a sore thumb. In year 12, Venus was absent from the sky for 166 days. That is completely out of the box. And in year 14, it was 45 days, a lot smaller, but that was, the 45-day one was an inferior conjunction. And if you work it out mathematically, it should only be about 3 days. So definitely wrong. That means that Venus was probably occluded by dust in the atmosphere, varying amounts, a lot in the 12th year and a little bit less in the 14th year. And I was saying, for example, that Santorini may have had 2 dates of explosion, a big one and a smaller one. And I also associated it with the biblical Exodus, you might remember, because there was a lot of research done to try to link that with the Israelites going to the Promised Land, because the 7 plagues of Egypt can be explained by a volcano going off. However, since then, they seem to have moved the Exodus a couple of 100 years into the future, leaving the volcano where it is. So I don't know how that stacks up, but I'm putting it in for completeness. I withdraw the comment I made in the previous talk, and I'm just leaving that now as unresolved, but it's not relevant to Babylon. Meanwhile, I went back to the web and I did a lot more searching for volcanoes. And I've read a lot of papers, but the one that's best for me to discuss just here at the end of this talk is the one written by McEnany and Bailey, and they published it in 2019, regarding volcanic activity in the 17th century BC, which is the century we're in, 1645. They report that the ice core composition at this date is not compatible with Santorini. And indeed, they go on to say it belongs to a volcano called Aniakchak in Alaska. Now, I hasten to add that McEnany and Bailey aren't the only 2 saying this. There's quite a lot of researchers in the volcanism who were saying this. But McEnany seemed to have the most up-to-date date for this volcano in their 2019 paper. So that's why I used that one. Now, why would this be so? Well, Santorini was a volcano that just exploded, like Krakatoa, as I mentioned in my last talk. When a volcano explodes, but isn't a proper caldera on a cone with sulfurous gases and all sorts of things coming out of it and lava flowing down, apparently when it explodes, it does not leave a footprint in the ice cores, because just dust goes everywhere. And so we're left with a situation that McEnany and Bailey are probably correct, and the other people that back them up. So I withdraw one of the lines on the tablet, and I'm happy to associate that with Aniakchak. But as I pointed out, there are two potential dates for volcanic activity, the 12th and the 14th year. So one is probably Aniakchak and the other one is probably Santorini. And indeed, in their paper, McEnany and Bailey hypothesize that Aniakchak has kind of saturated this, and that Santorini probably went off, within a few years of it. So it's all fitting into place. And the latest information I have off the web, which was only yesterday, it seems to change all the time every time I look at it. So this is quite a fast-moving arena. Aniakchak at the moment on the website is showing as 1645 BC plus or minus 10 years. Santorini is showing on the website 1610, on the volcanic websites, 1610 plus or minus 14 years. Now, if we look at Aniakchak, my result is that big 166-day occlusion of Venus is about 9 years after this. So it's inside this plus or minus 10 years. Santorini, I'm a little bit out. If you add 14 to this year, 9 years short of that. That's not a lot. I also suggest that we have to consider that these two should be reversed, that this should be 1633 and this should be 1636 to 35. Why? Because 1636 to 35, that's the big volcano, the one that took 166 days out of the visibility of Venus, and 1633 is the small one. What is the big volcano? Santorini. It was a volcanic explosive index of 7, and this is 6. So this one's 10 times bigger, and it's a lot closer to Babylon. So it's highly likely that when Santorini went off, a lot of dust arrived in Babylon. But when Aniakchak went off, a lot of its stuff went into the ice cores, and only a little bit of it, because it's in Alaska, and only a little bit of it arrived at the doorstep of Babylon. So we could consider these two in a different order. However, I leave that to the volcanologists. I can't make that sort of statement, but it's pretty obvious that we're in the right area for these volcanoes. So the above dates are compatible with middle chronology. I then looked to be absolutely sure. We know that the low chronology came second, and it was only about 50% worse than 1645 BC. So you might want to consider it. There's no suitable volcanic dates in current publications that I can find that are compatible with either the high or the low chronologies. So if you look at it, it's looking good for 1645 BC. So in summary, this is my last slide. I've said this before, it's my belief that the reason this tablet has survived and has been copied several times is because the Babylonians knew that 2 of the entries, namely those for years 12 and 14, were abnormal. And perhaps they were holding on to them because maybe in the future, somebody will tell them what went wrong with Venus. In the research that I've just described to you, I've used a mathematical procedure to get a result that's in the middle chronology. A procedure, as I've explained, that removes all emotion from me. There's no preferred date, no preferred data on the tablet, just numbers that I number crunched using a particular formula. Now, my result is 8 years different from a result of De Jong, who's been very active in this. He does a lot of very good work. He published a result in early 2000s that is the lower middle chronology. And McEnany and Bailey know of that actually because they refer to it in their paper. And it remains to be seen whether or not they were doing a bit of shuffling of their dates because they wanted to make it compatible with that date. I don't know. But perhaps this has got to be looked at again. However, I mean, I don't have a problem if somebody says, no, it's got to be 1637 BC. It's only 8 years different from the answer I got. And, you know, it's right in the middle chronology. So and finally, evidence seems to be stacking up in favor of a middle chronology. Thank you.
That's amazing. I think, can we all unmute and applaud Bruce for his talk? There goes the questions.
I've just stopped sharing.
Yeah, okay. Okay, do we have any questions on chat, or does anyone want to raise their hand? Is there anything on chat at the moment, Peter?
No, I think everybody's been stunned by the overwhelming information, but so there's nothing on chat. Anything on YouTube?
Nothing at the moment, I don't think. No. Does there anyone want to ask a question? Want to raise your hand or unmute to ask?
I'll ask a question. Bruce, this result, does it, I mean, how does it feed into the archaeological world? I mean, how do you take this and people say, oh God, this is great. What do I do with it now? You know?
Well, my impression is, and I've read quite a number of papers, of course, my impression is that the archaeologists, when they write a paper, they kind of hedge their bets as to which one of these dates might be right. And so there's a bit more text in there saying, if it's a low chronology, this will be the result, and so on. But if we can fuddle into one date, then the papers will be easier to write. You know, there'll just be one consistent historical list of dates. So I think it's necessary, shall we say, for this to be solved in some way. We've got to finish up with one date sooner or later. And all I'm saying is that without taking any preferred solutions, and just by putting a mathematical algorithm in there, that's the answer I've got. That's what I'm saying. Does that answer your question?
Well, yeah, but I presume having a fixed date or a relatively fixed date, other things will fit into place around it.
Yes, yeah, because they're interested in, as I said in the last, we've got archaeologists here, so I might go wrong here, but they're interested in the Hammurabi dynasty, and he's the important person in that. So if we can get Ammisaduqa right, we can get Hammurabi right. And there's also a date which is the fall of Babylon, I think. That's affected by the distance from Ammisaduqa as well. So there's some very important things going on in Mesopotamia at these times that they want to link together. And because there was more than one society in Mesopotamia, they can then also get a link between what those societies were doing at the same time and who might have met who.
Right. Nigel, I think that might address some of the question you were asking there. You want? You're muted. So.
Nigel, you're muted.
Yeah, thank you very much, Bruce. That was a fantastic presentation. You've kind of answered part of my question. Was I was asking if getting a date for Ammisaduqa helped did it help date other Babylonian events? But another question I'd like to quickly ask is, does it throw any, do your results throw any light on the way in which these observations were made by the ancient Babylonians in terms of how they measured these things, how they got their timings, how they got their angles and so on? What sort of instruments, what sort of buildings were they using?
I'm afraid the answer to that is no, I don't think it does. But I'm of the belief that what is written on the tablet could have been done entirely by visual, just by looking at what was going on. But there's a problem that you've just raised there that I'm aware of. This is Babylonian history is broken down, I think, to something called Neo-Babylonian history. And I can't remember what, I think it's Old Babylonian. Yes, I do think it's Old Babylonian. This is Old Babylonian history and not Neo-Babylonian history. And it's probably Neo-Babylonian history observations that De Jong took when he was doing his analysis about, you know, when it rose and set and what angles it might be at. But they know that in Neo-Babylonian times, that the calendar, the first crescent calendar, wasn't necessarily the exact day they saw the crescent on. They seem to have settled on it's going to have to be 29 days or 30 days. Now, because of the orbits, it's sometimes less, 28, 31. You know, the orbits, it's not a circle, the orbit, it's an ellipse, so you get odd results sometimes. And I think they'd settled on 29 or 30 days. So they would arbitrarily change the month, maybe even if they hadn't seen the crescent. And I read a paper on that, and it's quite, you know, difficult to read. But nobody seems to know if they did that in Old Babylon. So when I say I've got a precise Babylonian calendar, my calendar is not all 29s and 30 days. As I say, there's some 31s and there's some 28s, because that's the way it pans out when you do it with maths. I could probably write an algorithm that adjusted that, you know, so it's always 29 or 30. Be quite difficult actually, but even then you wouldn't know if it was the same as theirs. So that could be a complication. If they already were in Old Babylonian times, slightly massaging when that crescent was seen to keep the days fairly constant, 29, because 29.53, of course, is the average lunar synodic period. And so taking 29-day months and 30-day months is a good idea. Occasionally it'll be wrong because you got a 0.03 there, but they'll probably spot that. So we don't know. And I haven't found any papers that tell me what was happening in Old Babylon in terms of the creation of that calendar. And I'm creating a mathematically exact calendar.
Thanks very much, Bruce. Another mystery for you.
Hi, Bruce. We've got a few questions that popped up. Ramsey was asking, Ramsey, do you want to ask your question or did you get it answered?
I was wondering how the Babylonians observed the transit of the sun by Venus. Is that conjectured? Did they mathematically know it's going to happen, or did they observe it?
No. The point about the point that I'm trying to make at that moment in the talk was, and you're right, they didn't see it because you need a telescope to see it. But that table is used by researchers such as myself if we're looking for something that happened back in 1600 BC, because they've got the transits in their canon or their catalog. So in a sense, what Espenac was saying on that data was, if I project back everything that we know, there would have been a transit on that day, and I checked that my software gave it, but they wouldn't have seen it, no.
Okay.
Thanks.
Rona was next. Are you there, Rona?
Yes, I'm actually David, but that's okay. Hello, Bruce.
Hello. Yeah.
So I get it that you're saying 1645 is the favorite, but I'm not clear how much of a favorite it is. Does it stand out like a sore thumb, or is it just the first horse in a close race?
It's the second of the things that you said, but in view of the fact that there's so much resonance between all these orbits, the reality is you wouldn't expect it to win by a lot. And that's why I said at one point in the talk, you might want to consider 1581 or 1589, I think came second, because it wasn't that far away from 1645. But then later, when I looked at the volcanoes, I couldn't find a volcano associated with 1581 BC, or 10 years later, of course, was when the volcano went off. That means if you select 1589 as your year and you say it's not far behind 1645, I really like this year, you've got to explain why those two lines are on the tablet that are completely out of line, the 166 days and the 46 days, against something where there don't appear to be any events happening that would cause that, dust in the atmosphere or whatever.
How can you tell about dust in the atmosphere in the sense of, there's maybe other things other than volcanoes?
No, well, actually, the volcanologists have been quite busy for many, many years now. And you can go on the web, which I did yesterday, and there's a Wikipedia page that gives you the list of all of the volcanoes that they know about with dates against them. And that's how I knew that I couldn't find something in the 1500s BC or in the 1700s BC. These volcanoes are funneling in to this particular date. And I think it's a to and fro mechanism. I'll bet that McInerney and Bailey knew about, well, they did. They knew about what De Jong was saying and what others were saying about the archaeology of Babylon. And so when they're getting tree ring data, and there's also carbon-14 dating and the ice cores, and they were funneling into this same dates, it just adds consistency to the whole thing. I know it's circumstantial, but when circumstantial data comes up about fourfold in the one place, it starts to look pretty good.
Yes. Are you not assuming, though, that the thing that obscured Venus was a volcano rather than something else like a cloud?
Yeah. Oh, there's more in my paper, by the way, that you could pick up at 9 o'clock than I said in the talk. You're absolutely right. We could have been hit by a meteorite or a comet tail, for example. I believe that Egypt fell around 2200 BC. That's the first intermediate period, because it was hit by a comet, which put acres of dust in the atmosphere and gave them a major headache for several years. But so these things can happen, yeah.
Okay.
Thanks.
Okay.
That's the cross-examination over.
Yeah, we need to move on. Peter Cooper had an interesting question. You there, Peter? No, maybe he's gone. Anyway.
Right, I'm unmuted now, yeah? Right, my question is why did they observe these things? I've visited the Mayan ziggurats in I think it's in Belize, actually. And it's and also, of course, the Stonehenge, which enhanced, I think the general idea is that they enhance the ruler's power through their ability to predict future events. Is there any evidence, and presumably it also takes education, resources, etc., to even to create one tablet-sized set of predictions. So is there any evidence about why this evidence and these observations were taken?
Not being an archaeologist, I actually can't answer the question, because they may have discovered a reason. But if I were to give a reason, I would just say it's mankind. Mankind likes to know what's going on. And they will have observed that Venus was doing this particular course across the sky quite regularly. And they would eventually have decided that when it set in the west and rose in the east, it was the same object. So they just noted it down. In fact, one of the ways in which NASA knows how to take data back to pre-BC days is that they have folded into all their algorithms every sighting that they can find in antiquity. And so these sort of things would have gone in. Well, this one wouldn't have because it wasn't solved, but they've got material. And in fact, if you go back to, I think, was it Plato? Who was the one that discovered the Earth's precession? Somebody in 130 BC, wasn't Plato, I can't remember offhand who it was, actually worked out from data that had been around for 250 years at 130 BC, a very accurate value for the precession of the Earth's axis. It's said by some to be the greatest thing that's ever been done in astronomy, because it was done at a time that we didn't have precise instrumentation. And he worked it all out. Just from where, he worked it out, I think, from where stars were on the horizon, and they were drawn, you know, whatever, some 250 years ago, and where they were now, and he realized that they were moving. And that was precession. So we tend to think of the ancients as being, well, I won't say the word dumb, but, you know, as being people that were living in a world that they didn't know anything about these things, but they were looking at them and writing them down from antiquity.
Okay, we're going to have to, excuse me, Andrew, we're going to move on. Andrew Mackey wants to get a question in.
Unmuting. Thanks, Bruce. Another master class from you. And I've never been a mathematician, I never will. So to hear it explained carefully and progressively as you've done does me good for maybe about the next half hour or so, if I can hold it in my head. I'm wondering about the Babylonians' capacity in mathematics. You see programs on television where they investigate the way that they counted number and weights in the marketplace and how we learn from that. Apart from the astronomy, how good was their mathematics at these kind of periods of time?
I can't answer that easily, but recently, I think it was about a month ago, maybe two, somebody in Sydney, Australia, had decoded some of the cuneiform tablets, and he's proved that they knew how to draw a map of a local area and draw the lines where the person who owned a particular field were, and they had various fields, and they're drawn very accurately geometrically on this tile. So they obviously were working on quite a lot of fronts.
Yeah.
No, very good. And Andrew Farrow this time.
I don't want to put, I'm on mute here. I don't want to put Jeanette on the spot. But Jeanette is a researcher in this area. I don't know if you want to make any comments, Jeanette, on what Bruce has done, or any other questions?
Well, thank you for asking me. No, I don't really have questions. It's only what was said just now about drawing fields or so on cuneiform tablets. We have tablets about that already from the late Ur-3 period, which means very, very early second millennium. So that's already very old. And there are mathematical texts, many mathematical texts from the old Babylonian period, which is basically first half of the second millennium BC. So that's quite old. They did it all the time.
Yes. Thank you.
Okay, is that it, Andrew?
Yep.
Okay, Horst has made a comment. I think that was about who, I can't remember now. Horst, 130 sounds like Hipparchus.
The precession.
Oh,
yeah, the precession.
Yeah, thank you. That's correct. Yeah, I knew it wasn't Plato. He wrote books, didn't he? Yeah, Hipparchus. You're quite right, and it's heralded as being an extremely good piece of work.
And John and Ramsey have been having a discussion about how they might have been able to see the transit of Venus.
Yeah, I'm just going to say that I have a feeling that some of the people I was with
for one of the transits of Venus could actually see them through eclipse glasses. My eyesight isn't very good, so I wouldn't have seen it, and I was using a telescope. But I'm pretty sure Venus is big enough to be observed, but of course you've got to avoid being blinded. So I don't know whether they actually had the technology then.
They might have had a pinhole in a piece of paper or a papyrus or whatever, giving an image, and you might have seen it there. But then you'd have to know when it was going to happen.
Exactly.
Yes. The other thing I was thinking of, would they have seen Mercury being either side of the sun as well?
That sounds like another research project, John.
Yeah.
Thank you. Could you tell us when you'll finish that?
I'll start tomorrow.
Okay, thanks.
Okay, are we more or less finished now?
I think we're finished on the questions on the Zoom. Anything on YouTube?
Will, I think you're muted.
No, nothing to be added from YouTube, just the
Okay.
number of places. Which is good.
Well, thank you, Bruce. You never fail to entertain and stagger us with your maths and your presentations. They're all absolutely fantastic. Can we thank Bruce again for that? Just a reminder that the paper has now been published automatically. I assume even my web dev skills are up to scratch, and it is on a website at astronomyedinburgh.org, and it's one of the top news items that you'll find there. So you can download Bruce's paper, and it's got a lot of detail in there. If anyone wants to ask Bruce a question after this, then contact us through the same website using the contact form there, and we'll forward that on to Bruce, and I'm sure we'll get back to you on that. But thank you again for everyone for coming, and for our international audience. We've had some good comments on YouTube about this is amazing, absolute genius, and pure maths offering a practical solution to history. It's amazing stuff. So thank you everyone for coming, and we'll see you at one of our future talks. Good night.
Right,